Up next, we have Gyorgy from Riverlane talking about tangling schedules for easing hardware connectivity requirements.
Yeah, thank you so much. Yeah, so this is a joint work with Ophelia Crawford and Earl Campbell. Both of them are from Riverlane, and essentially I will talk about a method which we called Tangling the schedule of syndrome extraction circuits, which enables us to generate long-range entanglement on a hardware where we don't have that necessarily. And as a result, I will show you how to measure high-weight or long-range stabilizers on a square grid connectivity hardware, like a twist defect, for instance. So first, I will recall some prior art, and then I will present the new results. So as you may know, lattice surgery is a very popular and useful tool for fault-tolerant quantum computation. And typically what we do during lattice surgery is that, let's say there are, oops. Okay, so let's say there are two logical qubits, this Q1 and this other one at the bottom. The Q1 occupies this space on the hardware, and the other one occupies that space on the hardware. And we wish to measure a Y tensor X logical operator. So we can do this by lattice surgery, where the merge stage step involves a big patch, measuring the stabilizers for a big patch that connects the two logical qubits for the number of rounds typically. So in this lattice surgery example, this is the merge stage patch we have to we have, and you may notice that there are some local range or regular shaped stabilizers, like this weight for Z operator or this weight to X operator here, but also there are some irregular shaped stabilizers, like this elongated rectangle, this ZZ, or this purple twist defect here. So we are interested in this talk how to measure these stabilizers on hardware, and the naive approach is this, which you probably heard a million times already in this session, but let me just recall it. So we can appoint an auxiliary qubit, a green one, on each stabilizer placket, and then we may specify a schedule, which is here indicated by this arrow and these numbers, and that scheduling specifies for us a syndrome extraction circuit like this, where each number here just denotes the layer where we execute the entangling layer. So this is something which we can use for the twist defects and also for the elongated rectangles if we have the required connectivity. And by connectivity, I mean that two qubits are connected if and only if we can execute a CZ or a CX gate between them. So with this definition, we may compose a graph where vertices are qubits on the hardware, and they are connected if and only if you can execute, let's say, a CX gate between them. So here, on top of the patches, I showed the connectivity graph required with this naive syndrome extraction circuit method, and also here for the other patch. So let me now remove that. So these are the two graphs you have, but of course, you ideally would like to perform this lattice surgery operation on the same place, let's say. So therefore, you have to combine the graphs, and you easily see that it quickly gets a bit kind of awkward, which is hard to probably engineer. And it gets worse if you pose further very natural constraints on your hardware. For instance, we typically like uniform connectivity layout because you don't want to design a hardware just for one specific purpose. And also because of engineering challenges, typically low degree connectivity is preferred. And as it stands currently, it is upper bounded by degree 4 usually. So what we really would like to do is to execute these lattice surgery operations on a square grid connectivity hardware like Google Sycamore or Rigetti ASPEM. Okay, so let me recall two prior papers which address to some extent these problems. Both of them are written by the same authors, Christopher Chamberlain and Earl Campbell. So in the first case, they used twist-free lattice surgery on a square grid connectivity hardware, except here they introduced an area on the hardware, which they called a dislocation area, where, as shown here, the connectivity graph is essentially modified. So this requires you to design your hardware for a specific distance. So therefore, it's not ideal. But there is another proposal, which they called twist-based lattice surgery, where you can execute Y-based lattice surgery with a degree 6 uniform connectivity hardware. So where you have the square bit connectivity hardware and you have additional connectivities with horizontally adjacent qubits. So our purpose in this talk to remove this additional connectivity constraint, requirement, sorry. Okay, so for introducing our new technique, which we call tangling the schedules, let me recall first the scheduling rules. So here you have two plaquettes, an X plaquette and a Z plaquette. We have the schedules here, and they satisfy this condition A and condition B. So condition A is kind of a trivial thing which you always have to satisfy. All these numbers have to be different around a data qubit. And the other condition we call untangledness condition, which essentially says that like if you consider these numbers where the two plaquettes meet, either one should be, so this should be less than the other one, and in that case that should be less than the other one, or the other way around, but you cannot have something like that. And here in this case, as you can see, this is satisfied. But we figured let's check what happens if we break this second rule. So we call this tangled condition. So here you may see that the schedule between these two plaquettes is tangled. And you may see that if you push through the control node through the control Z, you obtain an additional CZ, which is between the two ancilla qubits. So this is a gate which is not directly available on the hardware, but you kind of generated it. So it turns out that actually, using a tangled schedule, we can measure the product of the two stabilizers without measuring the plaquettes separately. So just the product. So we can measure the XXYY ZZ weight 6 operator. So how it works is that you specify two schedules which are tangled between these two plaquettes. Then initializing in plus the auxiliary qubits, apply the entangling gates as specified by your schedule. And then instead of measuring out the auxiliary qubits in the X basis, you do that in the Y basis. And also you apply a Clifford correction. So it turns out that the joint parity of these two outcomes is the outcome corresponding to the product. Here you can see an equivalent circuit where we reorder the C knots. So they are in front of the CZs. Here you can see the CZ, which is kind of a result of this tangling the schedule thing. So of course we have a Clifford correction, and this Clifford correction is particularly difficult to implement on the hardware. So we don't want that, but it turns out that if you do 2 rounds of syndrome extraction or evenly many rounds of syndrome extractions, then the two Clifford corrections kind of combine together into a Pauli correction, which can be tracked in software. So if you use this method, you always have to do evenly many number of QEC rounds. Okay, so let me now show you how to measure the twist defect weight 5 operator on a square grid connectivity hardware, and then I will show you a method how to measure an arbitrary Pauli product for annotated planar code using lattice surgery. Okay, so this is the twist defect we would like to measure, XXY, XX. We would like to assume this square grid connectivity on the hardware. So we may initialize the 6 qubit here in the Y basis. And if we are able to measure the weight 6 XXYY operator, then we measure effectively the twist defect. So we may do that by appointing 2 plaquettes, a purely X plaquette and a mixed type ZZXX plaquette. And then define a schedule which is tangled between them, like here. This is a tangled schedule between the 2 plaquettes, and then you measure out in the Y basis the auxiliary qubits. So this is how it goes in practice for the twist defect. And it's very similar for the elongated rectangle. So this is one example how you can execute, let's say, a YYYY lattice surgery merge stage patch under square grid connectivity. So here what you can see, every plaquette which is red is X, and every plaquette which is blue is Z. If you see a point inside the plaquette, that means that the schedule between that plaquette and any other plaquette is untangled. Whereas where you can see an edge drawn, a line drawn between them, that means the tangled scheduling between them. So here, for instance, you measure their product. Okay, so this can be generalized to a general Pauli product. This is an example, and it turns out it's fault tolerant, so the effective distance of this merge stage patch is always d-1 at least given that the logical qubits have distance d. And this is under circuit level noise. So we performed some circuit level noise simulations with STIM. The details are in the paper. And I would like to finish with a conclusion. So just remember, if you ever experience connectivity issues, then the solution might be to start tangling. Thank you.